The objective of today is to learn the Black-Scholes theory. We had started last week passing to the continuum trading environment, and as a result of that, a very nice theory will emerge, which is what I'll present to you today. There's two aspects that I want to emphasize in the 3 hours we'll be spending today here. The first is we're going to build a beautiful building, mostly an academic one. This was a big revolution when it happened in the 70s, but that was a long time ago. That was in the 70s. The building still stands, and it's a very wonderful building, and I would like to show you some of the consequences of that, although we're not going to get into that. Today is the last lecture I devote to this topic. We're starting with risk management next week. The second is I want to, perhaps because we're building this academic entity today, which is very nice, I want to still underline the practical aspects of what we're doing. So I want to start with a question. It's a question for you. You don't have to answer, but I want you to think about it, which is, why are we going to continuous time? Why are we doing continuous time finance? We have a very nice theory, for sure, you're going to see. But why are we doing this? Are we doing this for the purpose of a theory, or there's another reason?
Typically, I guess, like continuous things for good approximations, when you have like a lot of evenly spaced data over a long period.
This is true. You're right. This is true. And the example I don't want you to ever forget is the example that I reviewed last week. The example of a good student who got very energized by seeing how you could build bigger and bigger trees with more and more frequent trading information. And then he wrote code. It was a long time ago, so it was not in Python, it was in C, I think. And then he saw it didn't work. It was code that he wrote for pricing trees that were in discrete time. They were not continuous time, they were discrete time. Yet they didn't work. The answer he obtained was a function of the time steps, because as more and more time steps were considered, he didn't know that his code would become more and more inaccurate. Okay? And this is a constant that happens all over math. In a certain sense, a lot of the continuous math that exists, and perhaps Newton was the first one to come up with these considerations, are the things that they help you understand the right scale of things. And then you achieve some sort of universal behavior that is going to, you need to understand it before you start to make things practical, because if you realize that something works at only this time scale, the time scale changes and then it stops working, you're not doing something useful. That principle that applies to engineering, applies to chemistry, applies to a lot of things, will apply here today. And that is the reason we're doing continuous time finance. So we understand one relationship where, if broken, everything falls apart. As a bonus gift, we're going to have a very nice theory, and I'll try to say some of the consequences of this theory. So that's the purpose of today. Now, the objective of this discussion on random walks was precisely so that we understand these things, how they work. So I have to give you a bit of a recap. Okay, it's a very fast recap of what we did. There's a very important dimensionality constraint that came up last week. And the best way to understand it is that if you have, or you consider a random walk to be a sum of individual coin flips or individual random variables of perhaps infinitesimal outcomes, then all of this leads, because of the central limit theorem, to a Gaussian distribution that has certain dimensions. We saw this last week. The result of adding infinitesimal coin flips like this is a Gaussian distribution that has a certain mean. The mean is not terribly important, but the standard deviation is important, and the standard deviation scales like the number of flips. Because of that, if we want this model to converge, we're going to have to take our infinitesimal outcomes to scale in a very particular way with the number of throws. And this is the scaling that works. We saw this last week. The scaling has to be, for the outcomes, proportional not to the time steps, but to the square root of the time steps. The outcomes have to be infinitesimally large compared to the time steps. If not, your random walk never leaves the origin. All right? That's the basic dimensional constraint that we need to respect. Everything is a consequence of this. You can think about this in an intuitive way, which is that sum contains a lot of cancellations. So it's going to be very small. You need to prop it up. You need to make it big. If you don't make it big, it's going to disappear because of cancellations. How big? Exactly that big, the square root of the number of. You need to increase its amplitude, okay? And that's the set of it. That's what we saw last week, and I'm going to take that for granted today. So we have the fundamental relationship, which is that dx is going to be proportional to the square root of dt. Now, this gives us into a. Once we've built this, we can create the theory of Ito processes. And what I'm giving you here is something which is very intuitive. I'm not developing the formal theory of Ito processes. This is something which, if you're interested in this, you can learn on your own, but not here. I'm just going to go very quickly through this. And an Ito process is a combination of these infinitesimal coin flips called Brownian motion or Wiener processes and the traditional deterministic drift that you find in Newtonian mechanics. So it's a blend of stochastic motion and deterministic motion. And Brownian motion in this case is this infinitesimal coin flip that gives us outcomes equal to the square root of dt with probability 1/2. But now, to this infinitesimal coin flip, we add a drift term that scales with time. So it's very small. The drift term is very small. Why? Because it's deterministic. There's no cancellations. You have to make it small, right? That cannot be big. Then you have a blow up in finite time. It has to be small because there are no cancellations. Ito processes are of this form, and they can be very, very general. Mu and sigma can be functions of anything. And we're going to see some examples of that today. I will just go through these things very quickly. But for the most part, we're going to assume that mu and sigma are constants. And with that, we can model the evolution of security prices. This leads to the creation of a stochastic calculus, where, again, the infinitesimal Brownian motion increments are proportional to the square root of dt. They have expectation equal to 0. After enough of these throws, we have a Brownian motion situation, and the marginal distribution at any fixed point in time is given by Poisson distribution of this form, where the variance is t. The standard deviation is the square root of t. Okay, so our distance from the origin will be like the square root of t. We can then turn this to model our stock price process. We are going to model not the price of the stock itself, but the logarithm of the stock. Why? For two reasons. Because if in doing things this way, we're going to have two realistic aspects to the stock price process. First, it's always going to be positive because I'm modeling the logarithm. So the stock price will be the exponential of some creature, therefore always positive. And in doing this, we're going to make the changes of the stock price proportional to the stock price itself. I'm talking about stock prices. You can apply this to futures prices. You can apply this to commodities prices, to Bitcoin, whatever you want. Prices typically change as a percentage of the price itself. And this model will allow me to do that. Is this the right model? Well, it's a model. Don't think that stocks have to follow this model. This is a model that satisfies these two important characteristics. There are many others. Why we're choosing this? Because we are starting. I'll introduce later other models have been considered, but they're all based on the same fundamentals that we're using here, relationships, variants of a Brownian motion. You can disperse with all of this and have your own neural network telling you how this, and that's a perfectly valid alternative model, and some people are doing that too. We're not doing that here now, we're doing this. The advantage of this is that this is going to lead to this academic edifice that I mentioned to you earlier, and some important consequences will be obtained from this. But this is because we assume this to be the price. Yes?
So how should I read this equation? It's the same x.
Sorry, I cannot hear you. You have to speak up.
How should I read this equation? So it says dxt.
This one?
Dt. Yeah, so is
Yeah.
it like saying an infinitesimal change in x at time t is mu times an infinitesimal change in t plus sigma
Yep.
times some white noises?
That's exactly what it is. So you can discretize this exactly as you said. Or if you look at the math textbooks, mathematicians never write these equations like that. They write the corresponding stochastic integrals, which are easier to express, right? But I'm not doing that because, again, this is not a course on that. So I'm going to appeal to your intuition. It may drive some mathematicians crazy that I'm saying this, but from a pedagogical perspective, it's the right thing to do for a course like this, because I have no more than half an hour for you to understand all these concepts. Then we have to get to work and see what this does for us in finance. But the actual formal derivation of this is with stochastic integrals. Okay, easier to work with. Okay, all right. So the stock price process for us is going to be this, as we mentioned. And this is going to now pose the question that, yes, the logarithm of the stock is an Ito process, but is the stock price an Ito process itself? The answer will be yes, and then the question will be, which one is it? Now, to do that, I'm going to pose a more general question that we're going to be using today, and that is, if I have an Ito process and I apply a function to that process, I modify the process through a function as nice as I need it to be, is the result an Ito process also? Yes?
So the price s is bounded above by 0. Shouldn't Ito processes always like grow indefinitely in that direction?
No.
No?
No. We're going to see that today. Yeah, we're going to see that today. In fact, this is one of this property that you're mentioning is going to be critical. We're going to need at some point processes that guarantee that things, for example, don't become negative. That's going to be a constant. For describing prices, for describing interest rates and other things, we will often prefer processes that don't become negative, for example. And we will be able to, this is one example, we will have processes that ensure that the solutions do not become negative. We're about to see one. We're going to see several of them today. Okay? So, but let me pose a more general question, because if I'm going to answer this question, I want to answer lots of other questions at the same time. And the question is, if I take an Ito process and I map it, is the result an Ito process itself? And the answer is yes, and we're going to find what it is. And to do that, we're going to develop a very important lemma, a crucial lemma to all of this, which is Ito's lemma. Ito not only created this theory, he actually produce the main set of toolboxes to understand it, and ethos lemmas are the core of that. Note that if the answer is yes, then I automatically have that the stock price will follow an ethos process by picking the function capital F to be just the exponential. Okay, so this is ethos lemma, and I'm going to do it in the simplest form possible. Simplest form possible. For that, what I'm going to be doing is this. Given an ethos, forget about prices now, okay? We're going to do a little bit of math, very, pseudo math if you want to. So if that's my ethos process there, then an application of the chain rule will tell me that if I have a function of x, that will evolve as what? Well, I apply the chain rule in two variables, right? But there's a surprise. There's a surprise because when you apply the chain rule in traditional calculus, you only get the terms in black. Why? And allow this poetic language. I will have to resort to poetic language. I'm not going to do formal math today. So in my poetic language, I would say that in traditional calculus, you will have to add the second order terms, but this is of negligible importance to either of these, so it disappears. It's not relevant. But today, because we're doing stochastic calculus, it's not true that this is negligible. When you take dx there and you raise it to the power 2, there's three terms that come up. Two are negligible, one is not. Which one is not negligible when you take the square of it? It's the square of dt. Sorry, the square of dwt. The square of dwt is dt. dt is not negligible. dt square is, and even dt times dw is negligible, but dw square is not because that's like dt. So I have to account for that, and that goes there. See? This is very interesting. This is very interesting. What's interesting is not that a function of an ethos process is an ethos process. We've seen results like that in math everywhere. Many families of functions, processes, variables are stable under transformations. What's interesting here is a surprise. We're picking up what? We're picking up something very interesting. We're picking up an additional drift. If the function that I'm using is convex and I'm picking up a negative drift, if the function that I'm transforming is concave. So the convexity properties of my function makes the drift change. Note that the stochastic component is what you would expect it to be. The surprise is in red. The surprise is in red. Let me tell you something philosophically related. The math is not exactly the same. Do you know why we have no smoking laws? Like at U of T, why you cannot smoke there? I mean, you don't smoke for many reasons, but why you're not allowed to smoke when you're sitting over there or you over there. If smoke followed a diffusion process, it'll take a long time for the smoke to get to us. So by the time the smoke gets here, we're all gone, we're home. There is a very interesting phenomenon which is called volatility-induced propagation, which is the volatility makes smoke travel faster than it would do if it was only for diffusion reasons. So there are there are situations in math where volatility gives rise to extra drift or vortices. This is one such example. You can think of it that way. Okay? Yeah.
So just to be clear, ethos by definition is something that looks like the x equals t plus.
Where mu and sigma can be dependent on x and time.
Okay, so but to answer the question of whether or not f of x and t is an ethos process, we have to express df expression of that.
Yes, yes. Yeah, so the answer is yes, it will be an ethos process where mu and sigma are functions of f themselves, and that's okay. That is allowed within. I didn't give you a definition, I like it that way. I have an hour to do this, so I gotta do it without definitions. If you want definitions, there are lots of books that will do lots of definitions. Not this course. Okay?
So
yes?
It's like the reasonable condition that has to be twice different as well.
Yeah. It has to be twice differentiable and so on and so forth. Yes. And measurable and who knows. Yes. Okay? All right, great. So that's what I said. The surprise is the terms that we have in red. This is a warning that we're not in Kansas anymore. We're dealing with stochastic situations which give rise to unexpected situations, like, for example, the mistake my student made 25 years ago. So now, this allows us to look at the stock price process, where if I start with my process for the logarithm and I apply Ito's lemma with the exponential function, that's what I obtain as the drift and standard deviation and volatility of my stock process. And by the way, this answer, I think, was your question. This Ito process makes the price never negative if it's positive to start with. Why? Intuitively, I can explain it as just intuitively, okay? Well, the proof is there. If everything I told you is true and you believe it, that's the proof, because that's the process for the logarithm. But intuitively, there's something very interesting happening here, which is, look at the if the drift is positive, right? Obviously. So if the drift is positive, there's a dt missing. There's a dt missing. If the drift is positive, then the source of negativity might be the stochastic term. But the stochastic term, look what happens. As S approaches 0 and is ready to become negative, the volatility vanishes. So the volatility will vanish. And whenever you have a process like this, there's always a rivalry between the drift, which is classical, mechanical, Newtonian, and the Brownian motion, which is stochastic. There's always a rivalry between them. Perhaps Brownian motion can win when S is large, but as S approaches 0, it's got to lose. It's got to lose because the volatility term vanishes. And as we will see, it vanishes very quickly. I will mention a result a little bit later, which is that if S is raised to the power 1/2 or more, S does not become negative. Okay, so the critical power is 1/2. For powers S less than 1/2, it could become negative, 1/2 or more, not negative. And this is going to lead to a number of financial models, which I will be discussing also towards the end of today's class. Okay, so I'm still doing math. I haven't done any finance yet. No finance, only math. Okay? We've just created the stock price process, as you have there. And now the dt is corrected, and you see the correct expression there. Okay? Now let me... Sorry?
What happens if ST is 0?
If f starts at 0, that's a very good... Well, the volatility is 0, so there's a 50% chance the process will become, I guess, I don't know, that the period will become positive and then never become negative again, or that it is negative and never becomes positive again. That's my guess, but I don't know.
Yeah,
50.
So it was just the equation you divided the
That's what that's what I think the answer is. But I actually, to tell you the truth, I don't know. I never thought of that. Yeah. Okay. Now let me give you a very interesting, not application of Ito's lemma, but let me show you Ito's lemma in practice. Okay, I have here an example that we will see later when we talk about investments. This will be an important example for us, but I'm going to introduce it to you today. Imagine I have a fund. I have a fund that I start with $1, okay, my hard-earned dollar, and I do great. My first month, I double my money. I go to $2. The second month, I don't do so well. I lose $1, so I go back to $1. But then the next month, I make another $1, I double my money again to lose it the month after, and so on and so forth. You see? Let me do a little bit of a calculation. If you calculate the return, the monthly return of my investment, what is my monthly return? My first month is I'm making 100%. My second month, I'm losing 50%. And then I make 100% again, and then I lose 50%. So I think I'm missing the month of January, but when I took the average of that, I get 25% per month. So my investment is making me 25% per month average return per month, which annualizes to over 300%. Would you like to invest in my fund? If I give you only the statistics, will you invest in my fund? Will you invest in a fund that gives you 300% per year? That's fantastic, isn't it? Well, guess what? The fund doesn't make any money. Why? Well, so, by the way, this is something that drives many people crazy, okay? And it's the people that don't understand math, because my definition of return does not say that I make money, right? Especially when I take averages. But that's not the point of today. We will discuss that when we look at investments. But let me look at this from a Ito lens. Look at my logarithmic return. My logarithmic return is log 2, log a half, log 2, log a half, log 2, yeah? It averages to 0, right? So think of it as the drift. This is not Brownian motion, but if this was Brownian motion, I have, for my log price process, I have a 0 drift and a standard deviation of 70% per month. If I apply Ito's lemma, what's the drift? Sigma squared divided by 2. What's sigma squared divided by 2? Ta-da! 24.5%. Remarkably close. Remarkably close. Okay? Remarkably close. So this is related to what I called a financial false friends. And there's one thing that is going to be now a constant for the remainder part of this course. The world of quantitative finance is full of false friends. You know what a false friend is? Something that looks right but is not. Okay? We're going to see a lot of things which look correct but in fact misleading. And when we look at the world, there will be a lecture on investments, which will be the second last Monday of March. That's going to be full of these. And the world of investments is, I like to say that Microsoft Excel is responsible for trillions of dollars of losses in the investment world. Because people tend to believe numbers. But people don't know what the numbers mean. So you believe numbers that look great. I mean, who cannot believe a graph which is beautiful and is in red? Right? Well, we'll be very, very critical of that. And I want to say one thing, which is the power of math in this area is not so much your ability to discover new things, but is to detect when someone is lying to you. Sometimes they don't even know they're lying to themselves, okay? So I think math is the ultimate nonsense detector, and this is what makes it very useful in this context. It's very hard to use math to create new things. Some people do it and they get the Nobel Prize. But in your everyday job, math is very good to detect mistakes when someone is just not doing the right thing. Like, for example, in this case. Okay, so with all of this, now I can turn into the Black-Scholes theory. Now I'll do finance. I'm done with my mathematical summary of what we saw last week. I don't think I've done anything. Well, yes, I've done one thing new. I've done Ito's lemma. That's new. The rest we already saw last week. Okay? I intended to end with Ito's lemma last week, but that's when my computer crashed. Well, just died. Lack of power. All right, so now I'm going to use all of this in a financial context, and I'm going to be doing math. So let's look at this. This is a bit of a mouthful. Let's. It's the 33-cent game all over again. The 33-cent game all over again. Remember the 33-cent game? How can you forget? We've been doing it every day for the last month and a half or something, right? Well, it's the 33-cent game all over again. I have my stock price process there. You may say, hey, wait, it was mu plus sigma squared divided by 2, right? Yeah, right. So I redefine mu, big deal. Different mu. This mu is not the same mu as 2 slides ago, okay? So if I did the stock price process for the, not for the stock price, but for the logarithm, what would I get? I would get mu minus sigma squared over 2, okay? All right? Okay. All right. And my option will have a payoff at maturity, capital T. And in fact, doesn't have to be an option, could be any derivative with an option. We're going to be assuming that my derivative option or whatever it is of European type. I'm not going to allow in this description early exercise. No. We wait until maturity. Okay? We did enough of early exercise with swing options and all of that. We're past that. So my objective is to find a price function which will be a function of the stock price and time, and a trading strategy that will tell me how many stocks to hold and how many bonds to hold at any given point in time, conditional on any value of S. And when I do that, that will be a replicating portfolio. In other words, at maturity, it's going to replicate my payoff, and the price at every point in time has to be, by absence of arbitrage, equal to my replicating portfolio. So I'm done with the slide. Do you recognize this is the 33-cent game? There's nothing new. I could have written this a month ago. In fact, 1 hour after we disclosed the mystery of the 33-cent game, I could have written everything we did that day like this, except maybe for that. It's exactly the same. How many stocks do I have at time t? Do you remember the 33-cent game? It was 2/3 of a stock, right? How many bonds? Minus 1/3. I borrowed 33 cents, right? That was my trading strategy. And when we had notes, I saw that at every note, what I do is I buy more, sell more, buy more, borrowing more. I sell some, I return some of my loan. Remember? Well, that's exactly what we're doing here. Except we're doing this now in continuous time, but it's exactly the same thing. So I have my trading strategy there. I have my replicating characteristic there. It replicates my payoff at maturity. And the consequence is absence of arbitrage. My derivative has to be worth exactly the same as the replicating portfolio, because they give me the same results every day. Perhaps the reason I could not tell you this 1 hour after we revealed the mystery of the 33-cent game is because we were still learning the implications of absence of arbitrage, which was fundamental for that. We were still learning that. But we've learned it well. We in fact saw the fundamental theorem of asset pricing, and I even gave you some hints so you can take that even to continuous time. So we are not heavyweights, but we have some expertise on absence of arbitrage. So this setup I have here should not be a big surprise. Yes?
How do you find the price, like the total price for trading strategy?
Okay. I think you're trying to ask a different question. So let me answer the question that I think you're asking, and then I'll go to yours, okay? There's something unusual here, which is I said I have a certain derivative, certain payoff, and then I'm saying I will find a price function. I said I will find a price function, right? And now I'm saying that the price function is going to be equal to that. So I'm saying I'm going to find that, but I already have the replicating portfolio there. So that's not what I'm doing. Maybe I should write this differently by saying I will find the replicating portfolio such that that portfolio I have there, that portfolio, this one without the F, that portfolio at maturity is the payoff. Therefore, the consequence of absence of arbitrage is that if that portfolio equals the payoff at maturity, prior to maturity, it has to be equal to the price of my derivative prior to maturity. So I could have written this differently, and perhaps that's your question. No, your question was different.
I was thinking, so this is a price function for each time.
Yes.
The price of the stocks and bonds, right?
Yeah. That's what I have there, yeah. So, okay, so let me make another attempt then. I think you're asking something that's not what I thought you. Remember when we did the European option 3 time step case, remember? The result of the price exercise was what? When we finished with our tree, we said, well, at maturity, this is the price of my option. And when the stock is $1.50 tomorrow, it's worth 75 cents. And so on. See, when I say the price when my stock is at 75 cents tomorrow, or $1.50 or whatever it was, tomorrow, I have tomorrow here, my second variable, and the first variable is $1.50. And the price we got was 75 cents. That's exactly what I'm saying here. That's exactly what I'm saying here. We've seen it before. And if instead S is not $1.50, but S is tomorrow, second variable, 75 cents, then the value of the option was, what was it? 12.5 cents. I still remember. You see? And then I'll go to today, so T is now 0, S is a half, the value is 33 cents, or whatever it was, or 58 cents and a third, or something. I don't know what it was. 58 cents and a third, I think. Right? So what we did back then on a tree, we're going to be able to do it now for all values of T and all values of S. Earlier, we were constrained. T could only be today, tomorrow, and day after. And S could only be $1 now, $1.50 and 75 cents tomorrow, and 2, 1, and 0 day after. That was my space of possible values. I'm taking this now everywhere. All times beyond today, not past maturity, and all possible prices. That's what we're doing. But it's exactly the same as the 33-cent game. You see? Did I answer your question now? Okay, good. So everything we have here, please note, is exactly the same as the 33-cent game. The only thing that I'm doing is, instead of giving you a stock price process, which was a tree with nodes, I don't have that. What do I have? That. Yeah? Maybe if I write on the iPad, it's better for the people on Zoom. Okay? But then I need my glasses. I don't want to continue until everybody realizes that this we've already seen. That replaces my stock tree. $1, $1.50, 75, 2, 1, 0. You may be thinking, oh, but that was not Brownian, or that was not... I know, that was not Brownian. But if I change, and that tree worked perfectly, and I had a trading strategy. But if I grow that tree with more intermediate trading times, that tree better converge to this. Or else, the results that I will obtain will not converge as I take more and more and more trading intervals. We've learned that. That we did not know a month ago. We know that now. We learned that last week. with that caveat that we have here. This is my stock price tree. That replaces my stock price tree. Huh? It is an infinite tree. It's a tree with infinitely many branches, infinitely many leaves, and hopefully infinitely many fruits. One of them should be you get a job or something. Yeah. Yes, Kavi. Yeah.
Mu represents like for one of the objects. Is it for a time period or is it like the
No. So the mu, what the mu represents is in our tree that we did earlier. If you look at the probabilities that I had, they were not exactly 50-50 going up and down. Okay. Or if they were 50-50, then mu would be 0. So mu allows me that the probabilities are not 50-50. It allows me to have, for example, what would be called an isotropic tree that tends to push me up more than down, or tends to push me up at the beginning and then push me down at the end if I make mu time dependent, for example, right? So the mu here is that in the trees that we did, the probability was 50-50. We very quickly learned to ignore the probability being 50-50, remember? It's going to happen here too, but we're not there yet. In the 33-cent game, it took us an hour to realize the probability was useless. It's going to take us here not an hour, but a whole week. We started last week, we will finish today. But we will also see that the mu is not going to affect our price. But it's exactly the same as in the 33-cent game, but it's going to require some additional thought. The result will be the same. Okay? So this mu, for now, it allows my tree to be imbalanced and to, push me up more than down or whatever I want. The drift takes me where Brownian does not. That's the whole idea. Okay? Good questions. Are we good with this? Yeah? You realize that this is the same thing we did a month ago, but now it may look different, but it's the same. Yeah? Good. So I'm going to see if when I realized that when I write on the iPad, for some reason, my presentation here gets out of focus and the clicker doesn't work, so I have to do it manually. Okay? I hope, yeah, there you go, manually works. All right, so by the way, I'll just mention one thing very briefly. This thing we're doing was known to a person called Bachelier. Let me spend some time talking about Bachelier. You may have heard that name. Have you heard that name before, Bachelier? Bachelier was a French mathematician, a student of Poincaré. He wrote his thesis in the year 1900s. People didn't think very much of his thesis because he was praising options. That's what he was doing. And praising options was not very popular amongst mathematicians. They would have been happy to do topology or to discover the laws of relativity, but options was not attractive. But he did it. And he did exactly what we did here, minus one thing. He had no financial argument. Poor Bachelier was alone. He didn't have a banker to give him advice. The bankers wouldn't have understood what he was doing anyway. We had to wait several decades before we understood what he did. And now we have the theory which is Bachelier plus corrected. So I'm going to talk about the missing piece in his theory. Okay, this is the financial argument. So I'm going to do, this is for us is fine. We're ahead of him already. Okay. So this is how we're going to be doing this. This is the financial argument. And look how I start. I'm going to say, assume the price function exists. Many of you are mathematicians, yes? Have you ever wondered why mathematicians like to spend so much time with existence and uniqueness theorems? No, have you wondered as a mathematician why we spend so much time in our lives proving existence and uniqueness theorems? Well, now it's under your skin. Well, I still think about that, Think of how much time we spend on proving uniqueness and existence, right? And people may say, well, why do you care to know if it exists, right? As a side note, in the 70s, when computers started to become very, very powerful, people felt the urge to calculate everything. I was very young. I was not part of these committees, but the committees of scientists that had to decide who gets funding, there was a condition that they had to apply, which is you only get funding if the problem you're trying to find has a solution. Many, many, many problems didn't have solutions. People were just, spending more and more money and more computational power looking for things that didn't exist. You could prove didn't exist. It's not you didn't know. No, this doesn't exist. So, throw away that computer, throw away that grant money. Just don't do that. And that happens. That happens. Okay. So it's very important to know that when we're looking for something, this something exists, right? It justifies all the effort that goes into that, right? Of course, there are some things that we don't know if they exist or not. The zeros of the Riemann zeta function, are there any outside of the critical line? We don't know, and we're still thinking. But if you know that they don't exist, then don't waste your time. This is what a mathematician would do, right? Now, in this context, I'm going to start by saying, assume the price function exists. I'm not going to prove to you that it exists. So I'm just going to say, assume it exists, and then I'm going to calculate it for you. All right? So I'm doing this in as careful way as I can, given the fact that today's lecture should be a course by itself. Okay? So I try not to lie to you too much, just a little bit, so we can get to the end of today quickly. That's one area. Okay? So assume the price function exists. And now, assuming that it exists, the advantage is that if it exists, I can give it a name. I'm not going to give it a Greek name, by the way, not this time. I'm just going to call it F. So if it exists, I'm going to, with the benefit of hindsight, this I'm only telling you, this works, and you're going to trust me, and I'm going to choose my trading strategy to be exactly this. It's the partial derivative of the function that I know exists with respect to stock price. You say, why that? Just follow me. Okay? After I'm done, you will say, of course, it had to be that. It could not be any other one. But I'm just going to give you this lucky choice for now. Okay? By the way, I'm going to make a very important mistake. Okay? I'll tell you the mistake only after I make it, not while I make it. Because it's my only way of going through this in 5 minutes. It's easier to fix these two mistakes, the assumption and then the actual mistake. Okay? So, making a mistake. But I have to. So now what I'm going to do is, given that I have this trading strategy, I'm going to consider the portfolio, which is my derivative, plus A times the stock. So if you go back to the 33-cent game, remember how we did that? I said, you pay me your 33 cents? Yes? And then I borrow a third, and I invest in the stock. Remember we did that? In 2/3 of the stock. I'm going to do things differently. I'm going to say, I take the option, 33 cents, and I'm going to invest. I don't know where the money is coming from, but I'm going to invest in a stock. That's what I'm going to do. The bond part I'm going to leave out. The borrowing I'm going to leave out. I'm going to do things slightly differently. Okay? It's okay. Everything is going to work the same, but I'm going to do it this way. Why? Because I'm going to apply Ito's lemma now. How does this portfolio evolve over time? Well, it has two things here. It has my option first and then the stocks that I have. And my option is going to evolve like that, but with that, because I'm applying Ito's lemma to it. Right? And then this is just that. And when I apply Ito's lemma, there's a term which is this one here. Okay, so this is Ito's lemma, where this is here. No, sorry, this is here. This is here. Okay, and all of that is this from Ito's lemma. That's all I have done. I've applied Ito's lemma. Okay. Sorry, say that again?
So I don't see why it doesn't A depend on T as well. Like I don't see why DT S mathematically is not.
Okay. So let's see. Let me see. What is it that you don't see?
I don't see. So you're applying DT to I.
Yes.
So you apply it turn by turn.
Yeah.
A also depends on T.
Yeah. So what you don't see is the A times S, right?
Yeah.
Exactly. So that's the mistake I'm making on purpose. Hold on.
Oh, I see.
Good that you caught it. Okay. I wanted to tell you after the fact. So let me just leave it there. Okay. I'm coming back to this. It's just that I want to. Kavya, you had a question?
I don't understand why the portfolio is equal to F plus A.
Oh no, that's my choice. That's my choice. I can invest in anything I want, Kavya. I can just I'm going to invest in this, and you will see why.
So, and F is the price function that we defined earlier.
Well, there's a function. It exists,
Oh, it's just
right?
A function.
There's a function. It exists. So I take that function, and because I live in a free country, I can go and construct this portfolio because that's my desire. Okay? Okay. And I do have to make a note of this. What's happening with this? He realized I made a mistake. But it's okay. Hold on. Okay. All right. Look at the magic now. The magic is that this thing and this thing, they kill each other, right? So the result is what? The result is that. So the result is that, except for this minor incident, this portfolio I have here is a bond. So if it's a bond, how does it change? It changes with interest rates, right? Okay, so that's the conclusion I wanted. Let me address what you...
The fact that it's like you say it is a bond, and the fact that conclusion is that there's no randomness at all.
There's no randomness. The randomness is gone. That's why I picked that. I picked that to kill the randomness.
So a stock with no volatility is a bond?
It's a bond. Yeah, it has to be a bond. Yes, it's a stock with no volatility is a bond, right? We saw that, right? In pricing, fundamental theorem of asset pricing, it's a bond. It just moves the way it does. Okay? All right. Now, so let me now come to your point. Where is this? Well, this is a bond too, because there is something which is called the self-financing strategy. Remember when we did our 33-cent game, multi-period? What did we do? Every time we bought and sold additional stock, we increased or decreased our bond. So there was a cash flow that went into the bond all the time. We didn't take extra money in or out of our strategy. It was a self-financing strategy. It always was. Okay? So the fact that it's a self-financing strategy is the reason that I'm not going to consider that term.
Technically speaking, the A doesn't really depend on T or something?
No, it does depend on T. What happens is that there's an additional. What happens? I'm throwing a number of other terms under the rug. That's what I'm. Okay, so this one, because of the self-financing condition, I need to assume that this term is going to be 0. That's the way I can explain this result in no more than 10 minutes. Okay? Okay. All right, so if I do that, now my portfolio is a bond, therefore this has to happen. And if this has to happen, by the way, this will be modified with the term that I'm missing there, but that term is going to be on both sides of the equation and it will disappear. It just makes my financial calculation a bit more complicated, so I prefer to ignore it. And now what I do is Lasitos lemma, and that's because of the construction of A. So these terms, they vanish each other. And now I go from my financial argument to a mathematical argument. So what I do is I go back to my stock part of the portfolio because I now know what it is. It was given by that. And then this portfolio has to follow what's called the Black-Scholes equation because this is what it's a bond. And if that's a bond, it has to satisfy this property because that's what the portfolio is. The portfolio is, that's the part of the the evolution of the portfolio, and that is how it moves. Okay? So if it's a bond, if this portfolio is a bond, this is how it has to move over time. So we rewrite this, and now it looks like a diffusion equation where the terms are written like this. I isolate my dt part of the expression, and everything else I throw to the other side, and that's what that equation looks like. And then I add my terminal equation, my terminal functional equation there, and it's actually a backward differential equation. This represents a backward diffusion. You see that the fact that negative sign there. So if this was positive, it reminds you of the heat equation. The fact that it's negative means that time is negative. We go backwards, right? Yes.
So this is just a regular PD.
It's a regular PD.
No more stochastic stuff.
No, it's gone.
So we started with something
Yes.
made a clever choice, and now
Exactly. Remember what we did when I described to you what Einstein did, that I also did it in 2 minutes? Remember? What happened there? There was stochastic movement of temperature, right? And they would say, well, if temperature moves in a stochastic way, then temperature evolves as a diffusion equation, namely the heat equation. We've done the same thing. That's what we have done. There we used a thermal argument, which is temperature moves half there, half there. And then, well, if that's how it moves, then heat equation arises. And here I've used a financial argument, except or modulo the self-financing constraint, which is, yes.
don't diffusion equations not go backwards?
Sorry?
Don't diffusion equations not go backwards?
Okay. So let's talk about this. This is very important now, okay? For those of you who know about diffusion equation, like the heat equation, right? You know how heat evolves. But you cannot move backward in time. If I give you a heat distribution now, there's no way you can know what it was yesterday or a second ago. There's no way to know. These equations are called irreversible. You cannot revert them back in time. The wave equation, yes, you can. Light, you know where it's coming from, but heat, you don't. Okay, if I give you a certain heat distribution, you don't know where that came from. They are irreversible, and that's what you're saying. Okay. The fact that I have a diffusion equation looks like the heat equation with my negative sign there means that this one is reversible. It's reversible. What I cannot do is solve it forward. Okay, this I cannot solve it forward. And by the way, that is why we filled our trees with backward propagation. The backward propagation for our trees was exactly the same argument that Einstein did for heat. He was going forward, we were going backward. Because ours is a diffusion process that goes backwards. Temperature and Einstein were moving forward. This moves backward. This is stunning. This is stunning. And you have seen, if you've taken courses on differential equations, this sounds very familiar, right? There's some interesting elements here. We've seen the negative sign. We know where that's coming from. Time moves back because I already know where we're going. I already know what the option will pay me at maturity. My question is, what does it pay me before maturity? So that's why I need a diffusion equation that travels backward in time. The other thing which is interesting is my diffusion term. Look what happens when S approaches 0. It disappears. It becomes degenerate. Okay? You may have seen the concept of elliptic differential equations. This is not elliptic. The Laplacian term vanishes when S becomes 0. A source of very interesting properties. People have spent their lifetime studying equations like this. We're not going to, by the way. Not that we want to ignore it, not that we don't respect it, it's just this is not our focus. Say that again?
Is it a different type, like parabolic, or?
It is parabolic, but it's degenerate. It's degenerate. But it's very interesting. It's very interesting. Okay, if anyone here loves differential equations and you're going to do a thesis, master or bachelor on differential equations, that's a perfect equation to. But if you're going to do this has been done so many times, don't do that. Okay? If you're going to do this, my advice is go high dimensions. Okay? And we're going to see some related stochastic processes today to what we're seeing. And there, if you want to do PDs, there still is problems that you can do. Okay? But make no mistake, in the financial sector, no one will care about your work. Okay? Academics will care, and you'll be the proud author of a very nice paper in differential equations. But in finance, this was important in the 70s, in the 80s. Now, I'll tell you what's important later. Other things are important. But this is good to know. And it's good to know because, as we will see later, this is not only a theory, this is becoming a language. Math seems to do that, right? When only a handful of mathematicians understand something is a theory and it's useful, but when everybody understands it, it becomes a language, which is, in a certain sense, what a lot of the machine learning, that's what it is. It's becoming a language, right? Okay, so that's that, and that is our terminal condition. Note that in agreement with my traveling backward, this cannot be an initial condition. It has to be a terminal condition. In other words, time is traveling backwards. Time is traveling backwards. Okay? And that's the Black-Scholes theory. I have to spend a little bit of time on this so that we've just climbed a mountain, a very tall mountain, by the way. And the view from here is amazing. I want to spend a little bit of time watching the view, the landscape from where we are. And then we'll take a break. Okay, so I allow you, please stay with me a few more minutes, maybe half an hour even, okay? It's worth it. We need to enjoy the view now before we lose, okay, when the adrenaline is still pumping. You do hiking in mountains? Yes? You do hiking? No? No? If you do hiking, you know what I'm talking about, right? When you get up there, you cannot get up there and then sit down and eat a sandwich. You can't do that. You eat the sandwich later, once you've admired everything. That's what we're doing. And then you eat your sandwich. Yes? All right. So this is good. This is good. We've done what Einstein did in 1905 by blending a very simple argument, in his case was temperature, in our case was trading, to understand how the price of options evolves over time. We've uncovered this. This was done, by the way, by Fisher-Black and Myron Scholes in 1973. Story goes that actually in the website you have the Nobel lecture of Myron Scholes. Is worth reading. He explains how this came about. It came from a consulting project of Wells Fargo, because options like these ones are part of compensation structures that companies give their top executives. I think we talked about that. And the question is, how much are they? And then he and Fisher-Black was a physicist, he was an economist, and they basically came up with this theory. But when they came up with this theory, story goes, I think it's true, they couldn't publish the paper. And they met Robert Merton, professor at Harvard, who they showed this result to Merton, and then story goes, Merton said, this is wonderful. He was working on the same problem. He had a different solution, so they beat him. And he helped them publish the paper ahead of him. Doesn't happen very often. Okay? So justice was done in 1997 when both Scholes and Merton got the Nobel Prize for what people wrongly called the Black-Scholes theory. Fisher-Black was dead, couldn't get it. Okay? We're going to we're going to see Merton's model. Merton had a reason, had a cause to do this, which is different from Black and Scholes. After this was done in 1973, in 1974, Merton wrote one of his best papers titled roughly The Value of a Firm, which we will do here, and that will be the fundaments of credit risk. You will see in about a month's time how this theory allows us to price a very interesting aspect of a company, and that's the right to default. We saw with the flight passes discussion how option pricing helps you price actions and whether or not you use your flight pass to fly to New York. There's going to be a wonderful similar situation where option pricing will help us understand the value of every company's right to default. You know, companies can default. They have limited liability as a legal characteristic. That's where prices don't become negative. Well, what's the value of that freedom? We will calculate it in about a month's time. At that point, we'll have to come back to this theory. We're not going to use it for a while, but we'll have to come back to this. All right. And this is why, at the end of this course, we would have been at all these many peaks, and then the view from each peak, when you get to see the other, they're all wonderful. We're going to climb maybe 4 big mountains. This is the first. Okay? This is the first, which includes the 33-cent game, includes this, and other things that we'll see today. And then next week is reading week, right? Yeah. So the week after, we're going to start a completely different mountain in a different country. Risk management, that's what we will be doing. Okay? We're following history. This was from 1973. Risk management, in a certain sense, started in 1987. I think we've talked about that, did we? I'm not sure. October 19, 1987. Do you know what happened? That will tell me if I've talked about this or not. October 19, 1987. The stock market crashed 25% in one day. One day. Recovered in a week or so. It was not a big deal. What happened? No one understood. You know, there was nothing there to indicate no crisis, no particular anything. It was the first case of computer-driven trading. Using these models, created the conditions for the market to create a collapse, 25%. And that was the beginning of risk management. That's when regulators decided that they better understand what all of this is about, because no one understood. And that's when real jobs for mathematicians happen in the industry. Not as traders, but as police officers. Understand? That's how risk management started. And that's what we'll start next week. By the way, next week we'll be on Zoom again. I'll be in Germany next week. Sorry? Sorry, the one after. Yes, the one after. I'll be, actually, no, we'll not be in Germany. I'll be in Germany next week, but I'll be in Spain the week after. So we'll have one session on Zoom. March 4th, I'm back. So March 4th, we'll be back in person. Okay? And I have no idea what I'm doing in March. I think I'm going to be here all of it, but I don't know. I don't know. Okay, are we good? This is worth admiring. I'm going to say a few more things about this. So the solution to the Black-Scholes theory, I mean, people know differential equations. You can solve this, and it's this. That's the solution to the Black-Scholes differential equation. When you look at this, what do you see? A big formula, big expression. Oh my God, look at that. Is that what you see? I see something different. What do you see? This is what I want you to learn in this course. I want you to be able to look at things and see the simplicity of everything. Well, this is the probability density, and now I give you all the information. What do you see? There I see a discounting factor, right? It's a discount. That's what I see. I have some future dollars discounted to today's price, and I use the discount factor for that. That's what I see.
Is that the exponential part?
Sorry?
Is that the
Yes, that's the exponential in front. That's the discount factor I see. Then I see an expectation. That's the integral. Then I see a payoff. That's the log normal price. It's just written in a very strange way because it's log normal, right? If it's log normal, that means there's the exponential of a Gaussian. The exponential is there. That's the exponential x, because that's where x is here. So this is the discounted expected payoff. Or in other words, this is the risk-neutral measure. We've seen it again. It used to be much easier, right? It used to be much easier. But it's the same thing, it's the expected discounted payoff. When we looked at the fundamental theorem of asset pricing, we were told that you can be given the wrong probability, it didn't matter. You can modify it. Okay, we gave you the radon-nicotine derivative, essentially that state price deflator. You can modify the probability, and then when you modify it, the price of anything is an expectation. That was the fundamental theorem of asset pricing. But this is it. This is the expected discounted payoff. Right? You see that? If you think this is complicated, please raise your hand immediately. Or say something on Zoom, because this is not complicated. You've seen this before. Kavya.
I'm kind of confused with the log normal.
Okay. So imagine that expected you see. Sorry, discounted you see, expected you see. And imagine that instead of here, I write x. F naught of x dx. Then you would agree with me it's expected discounted payoff, right? Yeah, but the expectation is the wrong one. Why? Because the price is not normal. This is normal. Look, the price is not normal. The price is log normal. That means that the price is the exponential of a normal. So you got to have an exponential of a normal. That's what I have. Then is the right expectation. That's the risk-neutral expectation. You see? Yes. Yeah. I actually forgot your name.
I was going to say, like, by definition, the variable is log normal.
Yeah, exactly. It's there. Exactly. Yeah. So is this clear? You don't need to know differential equations. You just need to know finance and the 33 cents game, because it's the same answer as the 33 cents game, just written in a seemingly awful formula, but it's the same thing. This is the 1/3 cent. And yes.
If you were to do the 33 cents game like a random walk, and you scale it like root n, like you scale it properly,
yeah,
and you took a limit,
yeah,
and you presumably get a Riemann sum.
you get that. Yes, you get that. Yes.
Because that's like how Ito was defined, right? The Riemann.
Very likely. I was not around. Ito is from the 50s. Kiyoshi Ito. But yeah, that's how I think he. Yeah. I mean, he took. This was not done in an afternoon. When I say, what do I do? I'm bored. This was the result of a lot of thinking and doing this, and this is the Riemann here. This is, right? This theory is very solid now. I mean, we're only scratching the surface, because most of you wouldn't have the background to do this very quickly, and you're not interested in this. That's my assumption. If I'm wrong, go and learn it yourself. My God, you can learn this anywhere. Go to YouTube. You'll be in an hour. You'll understand everything. But not here. Here you will see what I want to focus on. The landscape I'm going to focus here is the practical landscape. How are these things used every day? That's what's coming next. But first we need to understand every aspect of this formula. Every aspect. Expected discounted payoff. You don't need to know PDEs to know that this has to be the answer. You just need to understand the 33 cent game very well. Yes? Are we good? Let me ask you a question. Where's mu? No. R is R. R is the interest rate. Where's mu? Mu was the drift of my stochastic process. because the risk neutral measure is independent of mu. We saw it in the 33-cent gain. We saw it in the fundamental theorem of asset pricing, and it comes up again here. This is as good as it gets. This is the part Pacelli did not know. This is the thing that goes beyond Einstein. The financial element here that says that mu disappears. Mu is not relevant for the equation. It is not part of your trading strategy. It's not part of your price. Are we good? Is anybody lost? It's okay to be bored. That's okay. That's totally okay. Today it's okay to be bored. I'm not here for entertainment. I need everybody to understand this. We just climbed the first mountain to the top. That's it. There's nowhere else to go. You will see. We're done. There's nothing. We've been climbing every day. Every day was a little bit of a peak, you know. And then when you're there, you catch your breath, and then a week goes by, and here we go, another peak and another peak. Well, today we're at the top. That's it. This is the Himalaya. There's nothing else beyond this. There are no jobs here, by the way. Okay? We didn't come here for the jobs. The jobs start next week. Everything we do next week will be for the jobs. This is for the peak, because the landscape from here will help us understand where the jobs are. They're not in this mountain. No. The jobs are in a different mountain. Now, the jobs were here in the 80s. You knew this? You know, write down your salary and pick a firm where you want to work, and that's it. You're done. It's not like that anymore. Okay?
So no one cares about like this stuff, like the portfolio, like developing or anything.
You will see how we care. I want to give you a few hints now how we care, and then next week we'll start to do things that will actually get you a job. Are we good? I really want the whole group to be up here in this peak together, you know. Yeah? Okay. All right. So if I'm looking at a option price, a call option, I'm going to give you a very ugly formula, but it's important that I show you. With a price and everything, then the value is a function of 4 variables, which is the time, the strike price, the volatility, and the interest rate. Again, mu is not there. And it's equal to, well, some expression. Let me just write it quickly for you. That's the cumulative normal. And these are 2 well-known numbers. We're going to be good friends of these numbers in 3 weeks when we do credit risk, because now this is very useful for what Merton did with this. And that we're doing in 3 weeks, okay? But what I wanted to show you here is that this is something which you can calculate very easily. The integral is gone. It's all in the cumulative distribution of the Gaussian. And I have a 4-parameter expression, which is what is called the Black-Scholes formula for call options. Call options are going to be particularly important for us today, okay, in understanding the implications of this formula. Are we good? Okay, just a formula. It's there. I'm not even going to tell you where's the expectation of it. No, I don't care. It's just a formula, you see? Yes? It's a formula. You can forget it. I don't even want to explain the variables. Usually when I present the formula to people, I want to explain every variable. So I don't care. I just want you to know that there's a way to express the previous formula that is important in a way that any calculator can do, blindly. You can put this in Excel. Big deal. That's it. Done. Yes? Huh?
Sorry, I don't know how to use Excel, but Excel can use the Gaussian.
Oh, the Gaussian is a function which is there. Yeah. Yeah. Every computer has that, yes. It's no different from a gamma function or any other you want. It's all there, yeah. Or the sine function for that matter, yeah. How do you calculate the sine function?
I use the Taylor series. Is that what they do this one?
Sorry?
The sine function, I use the Taylor series. Is that what they do for this too?
You can do that. But the Taylor series for the sine, yeah, that will work. That'll convert pretty fast. Yeah. Definitely. Yeah, definitely. Okay, so now let me talk about European options. What can we do with this? We can definitely do European options. That's in fact what we showed today. Okay, European options have a certain payoff and a certain strike price. We've seen them many times, and now we put them into this general context, and with a certain payoff. I have a Black-Scholes price. Put options have a different payoff, and the same. I just put this into my Black-Scholes formula, and the previous one, the one with the integral, not the one that I just showed earlier. That's only for the call options, okay? And American options were the same thing, except they could be exercised prior to expiration. So I will have to modify my Black-Scholes theory to account for that. But I only need to modify the puts. The calls are the same. And I just mentioned a comment. It's not even written here in the notes. The comment is an American option. You remember that in our discussions, we never got to exercise them early. You know the reason? It's very obvious now. American call options never get exercised early. And the reason is the price never exceeds the payoff. Never. And that's by something called the maximum principle. Have you seen the maximum principle when you solve partial differential equations? The maximum principle says that the maximum occurs at the boundary. Well, the boundary is at expiration, so you never exercise them early. Put options do get exercised early, but not call options, and that's the reason why. Yes?
So that's like a thing that's true about harmonic functions, right?
Well,
okay. Is that because of this formula we know?
Okay, so you know the maximum principle for harmonic functions. That's what you see in complex analysis, right? Well, there are many maximum principles. They all come from the same area. They all come from the Laplacian. The Laplacian, and you've seen minimal surfaces, for example, right? They're all related to a property of the Laplacian. The fact that I have a Laplacian there is the reason. I have a maximal principle. I'm not going to go through this. It's not even written as a comment. But you understand what I'm saying, because there is a Laplacian there. And that Laplacian is the one that's responsible. Now we understand, because we've seen the diffusion equation. Now we see why we never get to exercise early. And if you buy an Air Canada flight pass, you never exercise it. There are other reasons not to buy the flight pass, by the way. Air Canada may watch this video and get upset with me. But I got very upset with them when I used to buy them. But there's a restriction there, which I did not know. They're only valid for a particular class of fares. If you want to pay more for the extra one, they won't let you. You have to use that one. And those fares are gone. There are seats. There are seats available, but not that fare. So I couldn't use them. So anyway, that's a different issue. And shame on you, Air Canada. The real world is a different world, right? So, but American options, they would have a price. And now the Black-Scholes equation is modified when you have American options, because you can exercise them early. The differential equation that we saw turns into what's called a free boundary problem. I don't need to tell you what this is, but I just want you to know one thing. You know the equations of elasticity. If I take a balloon and I fill it with water, is the typical example, right? And the shape of that balloon, if I fill it with water, is something you can calculate. It's a differential equation. What if I put it against the table? Well, the table pushes it up, so the equations of elasticity work except when you're touching the table. There's a different equation, right? Yes, that's called a free boundary problem. Then the pricing of American options in this context is a version of the Black-Scholes equation, but free boundary way. And when you put a free boundary, like in this case, if I put it, there's a very interesting. You not only calculate the shape of the balloon, but you also calculate the shape of the boundary touching the table. What that turns here is my optimal exercise boundary. Remember, those points say I exercise, I'm indifferent, I don't exercise. That gives you a boundary. That gives you a line, a surface, depending on how many variables you have. Is the equivalent of holding my balloon against the table. That physical process corresponds to this financial process here. Yes? Yes? The similarities are, you can spend a lifetime on this, okay? And some people have, but not us, not today. Okay, today I will finish all of this and then move to something different next week. Now, something very interesting, and this is perhaps the most interesting thing I want to say about the Black-Scholes theory today. I just checked the prices of the S&P 500 call option on the CBOE, the Chicago Board Options Exchange. Okay? And I have a question for you. So these are the prices of options. See, these are expire on February 16, which is in a few days. I have some strike prices, and I have some prices there. Are these prices calculated with the Black-Scholes formula? Where are these prices coming from? This might be the most important comment today, or the most important perspective of the mountain we just climbed. Where are these prices coming from? These are like the bond prices you used for assignment number 1. This is what people are willing to pay for these options. So the question is, no one showed them Black-Scholes? No, they know Black-Scholes. They know Black-Scholes very well. Black-Scholes is not used to price options anymore. Okay? Some, but very, very few. Very, very few. Most options are not priced with Black-Scholes. They're just priced because the markets are becoming very, very complete. You want to buy something, you can argue about the price. Well, someone already is offering a price. So what? You think you got an arbitrage opportunity because you managed to say that the price is higher or lower? What happens if you do that? These are the prices. I give you an assignment to calculate the Black-Scholes formula for that option. You say, oh, the price is wrong. The price is wrong. What's your conclusion if you say the price is wrong? No. So this is how the Black-Scholes price is used these days. Yes. Speak very loud. I cannot hear you, and the people on Zoom, they don't even know who you are. So.
I was going to say, I think they use the formula that we follow.
Okay. So the formulas have 4 parameters, right? Remember? One was the time. Everybody knows the time. It's there. The other one was interest rates. We all know interest rates. It's there. The other is the strike price and the price of the. We know that. How about the volatility? Who knows what the volatility is? No one does. Oh, wait a minute. I look at the 24-month average, blah, blah, blah. What does that have to do with anything? Market participants have a different view for what the volatility is than the result of some time series calculation, right? Something happens in a part of the world, the US trade deficit goes through the roof. Why does the number of 2 years ago matter? So these options which are traded, the Black-Scholes theory, it still uses, but backwards. We use these prices to get what the volatility is. And this is what's called implied volatility. And now this gets wonderful, because remember how we saw the implied probability, which was the risk-neutral probability? Well, it's the same thing for everything now. Volatilities too. People in the market, they estimate probability without any use of statistics, because the statistics have nothing to do with the volatility of the market now. The volatility of the market is given by the participants who buy and sell options at a particular price. Yes? In fact, you may have heard of a thing called a VIX. I call it a thing because a VIX is many different things. It's on the one hand an indicator of volatility, which is the implied volatility of put option prices on the S&P 500. It's also an ETF you can buy. You can actually buy stock volatility. Markets are so complete, you can even buy a statistical parameter today. I don't know, you can buy the 7th moment of the something, but the volatility you can buy and you can sell. It's traded. Go back to the fundamental theorem of asset pricing, where we said if I have a universe of securities, well, the volatility is there. And the Black-Scholes theory is what is used to calculate it. You can say it's wrong, it's not. I don't care if it's wrong, but that's how the volatility is given. You better understand it. You see, it becomes a language. When people say that the VIX is at 70 today, what does that mean? There's a Black-Scholes calculation somewhere that brings that number 70 as a consequence of what someone is willing to pay somewhere. That relationship between a price being paid for an option, which is real and is in Chicago, and the VIX being traded at 70, which is real, someone is paying $70 for the VIX index, that relationship, the Black-Scholes formation in the middle. That's what's so important to know. You see, that's a peak which is not even where we're at. We were in a peak where the objective of this mountain we climbed was to price options. Now we've seen that we have all of the option pricing techniques that we have, that we can wish for. Turns out that the business is elsewhere. We'll have to change peaks. We're only halfway through the course. We still have time. We're good. You understand what I'm saying? And like this, there's going to be many, many peaks that we can look at. The VIX is used as an indication of fear in the market. And it's a traded element. It's a traded security. It's an ETF. Okay? All right. And the VIX is usually comes up during bad times. You can say, well, good times should also make stocks go up. Well, no. Usually it's the other way around. Some more understanding to do. That's a peak we have not even touched. By the way, that is a peak we're not going to have time to climb. But many of you, probably 20% of you, if you become professionals in the financial industry, you will have to master that other peak that we're not going to even attempt to climb in this course. But we've climbed the main one, which is this one. This is the Himalayas, all right? The others will not be so hard if you understand everything we've done here. Let me continue with options that exist and that we could price with our theories. Bermudan options, where are they? Well, Bermuda, this is a bit of a joke. It's a real name. They're called Bermudan, but it's a bit of a joke. Because Bermuda is between America and Europe, right? So these are options that you can exercise whenever you want, but you're restricted to a few points in time. So it has something European, something American, therefore Bermudan. Could be called Cuban. They're called Bermuda. All right? So they also exist. There's Black-Scholes theory you can apply to them. Asian options, where are they? Asian options are options where the payoff, they could be calls, puts, but the payoff is not a function of a single value. Now, why would that be the case? And what does this have to do with Asia? Why are they called Asian? So the interesting here is, you see, the price is an average of prices. Either this, or that. They originate in Asia, and the reason is that Asian markets used to be very illiquid. So, say I trade an option with caveat on some Asian stock, right? And I'm Big Bang, she's a small consumer. And then I said, I don't feel like giving money to caveat. So I do a trade, a very tiny trade of a stock to bring the price down. I say, caveat, sorry, go. No, see? Call option, no, the strike is, and then the next day goes back up. I can manipulate the price. I could do that. By the way, I told you that we had this restriction. We're going to do everybody works for free. Yes? By the way, that's finished today. Okay? We're going to get into business now. No one works for free, and everybody's trying to cheat each other. That's the real finance game. We're going to have to learn how to do that too. So I have to tell you, the everybody works for free rule, it's finished. Absence of arbitrage, finished. All of that is finished. When we go to the other mountains, this is not going to be the case, right? So if I can, pardon the expression, screw you, I will screw you, right? I will move the stock, and then this is a defense against that. Because if I'm going to have to move the market to change the payoff of a certain security, I'm going to have to do that many times. Becomes more costly. Since caveat doesn't trust me because he knows that I can do that to people, then she's going to say, well, yeah, I'll trade with you, but not on one price, but for example, on the closing day of every day of 1 month. I said, damn, that's very expensive to manipulate the market so your option expires worthless. Very expensive now. But you're smart and you say, well, that's what I want. Okay, fine, I'll do it that way. So this is Asian because of that reason. But let me tell you where these things are very important. In areas where there are monopolistic situations. For example, if you want to trade an oil derivative with a very big oil producer, guess what? Who has market dominance over the price of that? You trade it in an Asian way, although you're not in Asia. It's a way to protect yourself from manipulation. See? By the way, this area of protection, these are different mountains now. We get to see them from here. But we're in the mountain where everybody works for free, everybody does what they're supposed to do, right? There's no way to make money. Well, that's finished. But again, the view we get, all those worlds from here is very interesting. And this is used for that too. I also have fixed income derivatives, and I'll end with this, and then we take a break. Okay, I have caps, I have floors. What are they? These are protection against the interest rates becoming very low, interest rates becoming very high, like calls and puts, but for interest rates. You have collars. Collars is you sell the cap, you buy the floor, so you guarantee the interest rate will follow a certain band. It doesn't, and if you choose the cap and the floor carefully, you can get what's called a zero collar, which is they trade, you buy them for free. You give up some protection here by selling some protection on the downside. For example, right? Then you have swaps. Swaps is I guarantee that I pay you a fixed interest rate, but then you pay me what is floating in the market. That's a swap. We exchange payments fixed for floating. And then have options on that. They're called swaptions. And then have swaps in different currencies, cross-currency swaps. And the thing just got started. The thing just got started. We started with call options and the 33-cent game, and this thing has like no end. From where we are now, we can see, I mean, we see the horizon is immense. But now we have a tool. We have a toolbox that allows us to go to all these places and do stuff. I'll end with the, it's called Greeks, the sensitivities. When I have a derivative, I will define the delta of the derivative to be the partial of the value with respect to the underlying, what's called spot. What does that mean? As the stock changes, that's what I'm going to make or lose. That's what that differential means. It also means that if I made a mistake, that is how my mistake is going. So this has many applications. The gamma is the second derivative. What does that mean? Is the rate of change of the first one. What would happen if you are, for example, if you have a call option, the strike is very close to strike, like the one we saw earlier in the Chicago listing, and you're right at the strike price, and it's maturity in February 16. The gamma will be what number? I'm appealing to your mathematical intuition now. That's all I'm saying. Mathematical intuition, not even financial intuition. You have an option, matures very soon, in 16 is what, in 3 days, in Friday. Matures on Friday. The strike is the value of the option now. Oh my God, if it goes up I make money, if it goes down I lose everything. The first derivative will be something. What is it, the first derivative, by the way? Mathematical intuition. What's your first derivative? No Python, no computers, no neural network, just thinking. Call option. You're at maturity. You're at the strike price. What's the derivative there? Oh, don't disappoint me. What's the derivative there? What's the derivative of this at the peak? Don't tell me it doesn't exist. No, that's not allowed. What is the derivative there? Oh, it's positive. Yeah, thank you. It's positive. Yeah, of course. But what? Equal to what? 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 Step function. A number. I need a number. I need a number.
I guess I'm confused.
What?
I don't understand what you're asking.
The delta. We saw earlier options on the Chicago Board of Exchange, the Chicago Options Exchange, and we saw that they mature in 3 days. And I'm saying if the value of the stock is the same as the strike price, what would that delta be? Huh? No. No. If the stock is at the strike price and the option matures by Friday, what is the delta? It's a half.
Wow.
The derivative of this is a half at the peak. It's plus 1 on the one side and a 0 on the other. It's a half. The delta is a half. How about gamma? Gamma is infinity. Gamma is very large. If you are trading, you have to know these things like this. All right?
Sorry, how is it infinity? You just described a straight line.
No, it's a straight line, but then it's 0. It's just 1 and then 0. The payoff of the call option is 1 and then 0. Right? So the derivative there is a half. 1, 0, a half. But
At what point is it a half?
at the strike price. We're at the strike price now, right? So of course, at maturity, the second derivative is infinity. So today it's going to be very large.
So the slope of the call option would always be always have a derivative of 1 while it's
It's 1 on one side, but it's 0 on the other.
so it can never be 2, it can't be.
No. Caveat. The call option. Okay, I'll draw it here. Oh no, you're hurting my feelings. I thought you would know this. Okay, so this is the graph of a call option. Yeah? Of course, that's at maturity. We're very close to maturity. We're almost there, right? You know diffusion equations. You're very close to the start, so it's going to look like this, right? It's going to look like that. I guess that's going to look like that. So the derivative now, if I'm close to the strike price, is a half. That's the derivative. It's a half. And what's that? It's red, right? If you're close to the corner, that's gonna go to infinity as we approach expiration. We're gonna see this gamma blow up, and this is a big deal because you can lose so much money if you're short options. Short option trading is a weapon of mass destruction. Okay, so many funds are blown up because of that. We'll see that next week, right? So short gamma, close to expiration, very dangerous. You can blow up your entire portfolio. Why? Because the derivative there is infinity, right? If you're long option, great, it's infinity. There's a chance I make a lot of money. You're short options, you're selling options. You're close to expiration, my God, there's a chance you're going to be wiped out, right? These things are very important. We're going to start risk management next week, right? All these things matter. All these things matter. Let me continue. Continue. Okay, you think about this, okay? You think about this. Okay, it's happening here.
So can you leave the picture up?
What?
Can you leave the picture up and label it? I just don't see how you're going to get infinity for gamma. You have a corner.
Yes.
Okay, I believe that near the corner the derivative is a half, but everything's a straight line. I don't see how the convex nowhere is this function convex. At the corner, it's not differentiable. So
Exactly. No.
You can say it's infinity. You just can't assign anything to it.
Well, that second derivative, as I approach expiration, okay, if the stock price continues to be the strike price, that goes to infinity.
If you looked at a series of smooth functions that were approaching that corner,
Yeah.
the second derivative would have to blow up.
Exactly. Second derivative will have to blow up.
I see. Okay. So
Yeah. I'm giving you food for thought, okay? I'm trying to develop your intuition. I'm trying to get you to see from this peak what is in the other peaks, right? This is what we've gained. We've gained a tool that will allow us to see lots of things even from, in a distant peak somewhere else, right? And all of this is going to happen, is going to start to happen next week. Here's Vega, a very well-known Greek letter, right? It's not a Greek letter. Anyway, that's the derivative of my option price to respect to the volatility. That's a very important one because no one really knows what the volatility is.
Did you use new word, call it Vega?
Yes, that's how it's done.
That's
Yeah,
okay.
that's what it is. That's what it is. That's what it is. That's what it is. Yes, that's what it is. Why these things are called delta, gamma, vega, I don't know. I have no idea. Let me continue. There's more. There's the rho, which is the derivative with respect the sensitivity to interest rates, right? Like the Fed was raising rates like 4% in a year. What is that going to do to your portfolio? That's what that's going to do to your portfolio. So you see, we now see the world of risk management from where we are, because we have explicit control over those functions there. It's just that it becomes much more difficult. And then finally is theta, which is the sensitivity to time. So it's the time value of the option. As the option, as time goes, your option starts losing value. That's theta. What is this? These are derivatives of my portfolio value. This is very important in finance, because how do I determine if I'm going to make or lose money? Starting next week, we'll start to talk about making and losing money, as opposed to just prices. These are differences of prices, right? Yeah? Differences of prices is more difficult than prices themselves. Imagine I was to measure my weight by measuring the weight of the earth with and without me, and then I take the difference. That's exact. Yes? Good luck doing that calculation, right? So that's why if you approach risk management from a simple-minded perspective, you don't know what you're going to get. This perspective will be very useful to approach risk management. A bathroom scale is a derivative. That's how I can measure my weight without measuring the weight of the earth with and without me. You see? This is yet another peak that we can master, and that, by the way, this is the peak where many of you will be working. Many of you will be working there. Yes, I can answer your question now. Sorry, I couldn't.
Okay, I understand this, like, this comment now that you're approximating this piecewise linear function by smooth function.
Yeah.
But so is it beneficial then to think of these things as distributions? Like, because yeah, okay, if I have like a piecewise thing and I take the
Except, well,
step function.
except, yeah, okay. So that is a good question, and it's related to the question I think he answered earlier. So why do you worry about gamma? This is not an academic concern. My concern is February 12th, options expire on the 16th. I sold a whole bunch of those options. How bad is it? How much money can I lose, right? And I need to know how much.
But that's sort of secondary. I'm just trying to understand, like, how, just from like an intuitive perspective, as someone who has done math and not economics.
Yeah.
Is it beneficial to think this second
No.
derivative as a giraffe math? Like,
No.
say it's infinity or something?
Beneficial to a certain point, because, I mean, beneficial. So beneficial for what? There is an objective, which is how much in trouble am I? Can I measure how much in trouble I am? I'm Silicon Valley Bank. Damn, rates continue to rise, right? Am I in trouble? These are the questions that people need to ask. I need to have an answer. That's all I'm talking about. That's what we will do next week. Okay? You're concerned about the mathematical inexistence of the second derivative of this function. Not relevant. Because this is a diffusion equation, and I'm looking at this from still 2 days. A diffusion equation, when it comes to regularity properties, 2 days is an infinity. 2 seconds is an infinity. Well, yeah, but not for my portfolio, sir. My portfolio could be in real trouble. And that is what these things will give me. So risk management, equipped with the tools we've developed in this first month of this course, we have hope that we can do something. That's what we will do next week. Again, I'm taking a peek at a different peak. You understand the 2 peaks? No pun intended statement that I just made. Yes? Okay? But we see it. It's right there. We're just in the wrong one, because here we were just pricing. And there in that peak, people are busy calculating differences of prices, which is what blows up banks and portfolios and pension plans and who knows what else. And differences of prices is not the same, oh, I do this price and there this price. No. You need a whole new theory for that. The theory of differences of prices is not based on the theory of prices. We've been working on the wrong problem if that's what you're worried about. You need a bathroom scale, not a way to measure my weight with and without the earth and take the difference, if you follow my analogy. Yes? All of that is what we'll do next week. I'm just trying to justify these things. These are some graphs over time of these things, and that's it. So this is the break. This is where I wanted to end today. We're going to take a 15-minute break. I think we need it. Now you can have that sandwich, okay? We've taken a peek at the landscape. When we come back, I'll show you some other peaks. And then that will be the end of all of this. You'll see, actually, not only peaks, you'll see universes, entire galaxies, okay? And that will be the end. Next week, we'll start with something completely new. 15 minutes, you need it, okay? And thank you for coming to this peak with me all together. Yes?
Are you going to be posting these slides, by the way?
Yes. Yes, I have to. I owe you a number of slides. I'll put them on the website also. And it's interesting. This year I have many more views of the videos on the YouTube channel than any other year. Order of magnitude, I don't know. Are you guys watching them or someone else? I don't know. Sorry?
Still got taught by the algorithm or something. Other people that must be watching.
It's very, very large numbers.
The bubble.
Let's see. No, it's okay. Okay. Yes, I'll post the slides. It's just these days I've been literally drinking from a fire hose. And as you can see, many of these things are new, things that I have not done before. A lot of that is because, as you can see, a lot of this is material that I've done for FIT. So that now I have a lot of material, and that allows me to. Oh, by the way, a note before I start. Someone registered for the FIT with the Fields discount code, and I think it might be one of you. The email address that they used is wrong. So that's what I want to say, because there's no way to reach this person because the email is misspelled. So if anybody registered and you're listening to this, reach out to me because you mistyped your email address. Okay. Okay. Continuing with my perspective, we've climbed the Black Scholes mountain, big mountain. The landscape is already looking good in that direction. I want to look into the landscape in other directions. And that's all I want to do in the rest of hour that I have. Just from here to get you to see things that we're not going to do in this course, things which are very important, but I think it's not worth going there. We have more important places to go, and that's what I will do. But since we're here, I have half an hour, why not spend time showing you what else is there. The first thing that I want to do is we discussed Brownian motion in a very, how can I say, in a very descriptive way, without any regard for any formalism. I think for what we want to do, this is good enough. But maybe I want to say more things about Brownian motion. By the way, you know the name comes from. I probably said this before. I'm not sure. Robert Brown, a botanist, who was studying things, and Darwin used his theory on his language, actually, not the theory, the language on his book, and then Einstein came in 1905 and did what we already presented here, so this we already know. But I want to give you some technical stuff about Brownian motion, which I will need. I will need something more about Brownian motion, not related to stock prices, but related to investments. So since I'm here half an hour, I'm going to tell you some other things about Brownian motion that will be important. So there's two notations for Brownian motion, W and B. These are traditional notations. B for Brown, W for Wiener, Norbert Wiener, who is the mathematician who mathematized all of this with formal language. Mathematicians tend to use the term W. People in finance tend to use the term B. Big deal. Not important. Not interested in that. So Brownian motion has the following properties. First of all, that's a mistake. It's it's the, well, it's not the W which is 0, it's W is 0, it starts at the origin, okay? So that's it. It's a trivial mistake. And then the definition of Brownian motion is a stochastic process which has characteristics and it exists by the theory of differential equations. And the increments between two observations are independent of each other. That's a very important property of Brownian motion. And not only are they independent of each other, they're all identically distributed as Gaussians, where the variance can change depending on the time scale. So the variance grows as the square root of t. Therefore, the difference between two Brownian motions is a normal distribution with a variance equal to the difference in time, okay? Or the standard deviation is the square root of the difference. All right. There is a theory that says that this thing exists. We're not interested in that as usual. We're interested in what we can do with this. And the paths for Brownian motion are continuous with probability 1, and they're differentiable with probability 0. This has, now I want to propose, an example. Imagine I ask you to calculate what's the probability that Brownian motion is less than or equal to 0 in 2 minutes. 1/2, exactly, very good. So this is 1/2 is there. Now if I ask you what is the another probability, the probability that is negative less than or equal to 0, now is 0, so it's fine. But today, sorry, tomorrow and the day after. How would you do that?
The value of WT is necessarily dependent, right?
They are, that's right. The values of the WT are dependent. It's the increments which are dependent. So this is a mistake, a typical mistake. What you need to do is, so the answer is not a quarter. Okay, that's a mistake. I could do this as a question. I didn't want to. I prefer to explain. Okay, the answer is not a quarter. What you need to do is you need to write W2 as the sum of two independent Brownian quantities, and I have them here in front of you. W1 and W twiddle 1 are different, but they're identically distributed, and those are independent because W2 minus W1 is independent of W1 minus W0. So that's what you do. That's how you have to do it. Now, since these are independent, what you need to do is you need to write down the problem that you have as this. It's a long set of integrals, but that's how you do it. Okay? We're going to need things like this later. So since I'm here, I thought I would mention this briefly. The way to do that is, so you use the W twiddle, not the W2 that we did. So it's here. Yeah, that's the one we use. And these are independent. So this is how you would calculate that, and that is an integral where W1 is distributed as a normal variable, and then you just follow your nose until you get to the answer, which is an eighth. Okay? You may have seen this in this statistics course, which is a core requisite to this. You may have seen these things out there, but I wanted to make sure because some of these things will become important later on when we do investments. Okay, so now in dimension n, the definition is the same. It's just that everything becomes a vector. My Brownian motion is it starts at the origin, and then it has independent increments, which are multivariate Gaussians. We didn't do the Black-Scholes theory in the multivariate case. It can be done in the multivariate case. Everything carries the same. Brownian motion in the multivariate case is the same. And the increments are distributed as independent random variables with that covariance matrix that you have there. So far, so good. Now, when we say that this is true, the difference of Brownian motions is the normal distribution with that variance covariance. Yes?
Is it true that each of the components is just going to be a one-dimensional?
Yes, they have to be, yes. So that's actually what I'm saying here. Okay, so the marginal increments, okay, being independent across time, across marginal. So if you have Brownian motion as a vector, each of the components is a Brownian motion too. Okay, And as with one Brownian motion, sample paths are continuous with probability 1 and differentiable with probability 0. Fine. Correlated Brownian motion. This is a generalization of Brownian motion that you can do when you can assume that you can make the you can have a correlated Brownian motions, and the easiest way to construct them is if you're given a variance-covariance matrix that you want it to be your Brownian motion, is just take your Brownian motion vector and multiply by that variance-covariance matrix, and this is the result that you want. Okay, it's very simple. You do that with matrix multiplication, in which case the difference of Brownian motions, the increments are distributed as normal random variables with a given variance-covariance matrix, but still it scales in time the right way. That you cannot change. That you cannot change, okay? And the independence of increments is also another thing you cannot change. You cannot change the time scaling. You cannot change the fact that the increments are independent. That cannot be changed. If you change that, you have an entirely different process. It's not within the realm of Brownian motion, okay? How you calibrate Brownian motion? If I give you a set of observations. So in dimension 1, if I give you some observations, how would you calibrate it? So very simple. The mean is, I look at all possible increments. You can take not only the nearest neighbor increment, you can take all of them. Okay, nearest neighbor, it's up to you, but you can take all of them, and then the mean of that will be the drift of the Brownian motion. And once you have that, then you construct the sequence, which is the normalized version. Now that you know the mu, and the result will be the standard deviation, or in the higher dimensional case, the variance-covariance matrix. Okay? So this can be calibrated. Now, one thing that I did not do, and I don't know if I'm going to do it, is the opposite of this, which is the generation, which is called the Monte Carlo method. I will do that at some point, okay? At some point I will tell you how Monte Carlo methods are done, which is the opposite, to actually generate these things. One thing is to say, oh, it exists, and how do you do it? How you do it, okay? Of course, there are packages that do them, so you don't, in principle, you don't even need to know. But there are some considerations, so I'm undecided if I will. I used to do Monte Carlo in the past. This year I'm not doing that because I want to do other things, but I may do that later on, okay? If not, I think you have the Monte Carlo notes on the website. You can just read them. It's not very hard. The interesting aspect of Monte Carlo is how you generate random numbers. That's the very interesting one, but okay. And so after this, the next step would be to deal with Brownian motion with drift. We have assuming that Brownian motion is not going anywhere, it stays stationary at the origin, but of course you can add a drift to that. We've seen that, we've seen the ATO processes, but when it comes to Brownian motion, it's very simple. You just add the drift, and it could be given as a function of time, and you have Brownian motion. This is very simple, very simple. And then you can see that the increments of Brownian motion, they are given by this, okay? So linear transformations of Brownian motion allow you to come up with a wide variety of stochastic processes that have nice properties. The one important thing, and I said earlier, the one thing that you cannot touch is the increments of the increments being independent. And this is very important. This is related to the phenomenon that we called lack of memory, I think. And it's the one that has to do with the trees that we are recombining. Remember when we started to do multi-period finance, and I presented the case of a tree that was not recombining, and then we did a calculation of forget it, that will not be useful because we run out of memory very quickly. The remedy does to do the recombining trees. Well, there is a version of that which follows mathematical thinking, which is that I need the Markovian property. I need the lack of memory. Models without the Markovian property are very, very hard. There are some in finance. There are some. But people tend to mostly stay away from them now because they become very expensive. Okay? So that's important. We need to keep the increments independent. Brownian motion has properties. I'll just walk you through this. This is not very important. They're additive, so the sum of Brownian paths is a Brownian path. And the variance covariance matrix is, and the mean is what you exactly would expect it to be. In the case of independence, okay, very simple. In the case of independence, now, if they are correlated, this gives us some difficulties. If they are correlated and the increments are jointly Gaussian, this is very important. Remember, vectors, random vectors, could be Gaussian, the marginals be Gaussian, be correlated or uncorrelated, and not be jointly Gaussian. So here I'm talking about being jointly Gaussian, okay? If they're jointly Gaussian, then I can calculate the variance covariance matrix of sums of Brownian motion too. But they have to be jointly Gaussian, okay? Most often, these Brownian processes are not jointly Gaussian, and we use other ways to understand the processes that arise. They are not Brownian motion anymore. And that's where you introduce the concept of the copula, which I'm not sure if I will show you, or we'll discuss it. Maybe I do, maybe I don't. I haven't decided yet, okay? The multidimensional aspect of all of this is very tricky. Scaling, if you have Brownian motion, you can scale it in this way. Yes?
When you're talking about like WT being jointly Gaussian, we're saying for different times it's jointly Gaussian, or sort of the different...
The increments for different times are jointly Gaussian, yes. So the increment between, say, today and tomorrow and the day after, jointly they are Gaussian. Okay, so the scaling, if you take Brownian motion and you scale it with a parameter, you see I have to respect the dimension, the time dimensions. We've learned that, right? So that's Brownian motion too. These are some mathematical properties of Brownian motion. Time inversion, not very interesting for us. I don't think we're going to use that, but you can change the clock in this way, and then the result is Brownian motion too. So Brownian motion is, you can go very far. You can do many processes that use Brownian motion. So everything we've learned is easy. You can do that. Now, here's an important point. This is what I wanted to get, and I will end with this. Heating times. Heating times is when you have a stochastic process, the heating time is the first time you reach a certain point, and it's a random variable. You don't know what it is, okay? For Brownian motion, this can be calculated explicitly. It has many applications. We're going to see one in investment management today. We'll make full use of that 2 or 3 weeks before the end of the course, okay? But for example, ruin is an example of a heating time. Ruin is when you reach zero money, right? It's a heating time. So you bet heating times are important in finance. Huh? And in this context, I want to remind you, I don't know if you've seen this, it's called the reflection principle. The reflection principle is a property of heating times, tells us that the probability that I'm at a point higher than x when I was already at x earlier, the probability is a half. And the best way to intuitively think is that, well, if I was already at x, every time I have a path that ends above x, there's one that ends below x. I know there's infinitely many. You cannot just count, but if you could count, that would be the yes.
Can I understand this like this? What was mentioned that the probability that you're above zero is half?
Sorry?
It's basically like the probability that you're above.
Yes.
Do you know that at one point you're
Right. So it is a generalization of that. But you see, it has a very important consequence, which I want to express today, because we're going to generalize the concept of ruin, and I will need this for investment management a few weeks later. So I'll tell you now and then. So this is the picture. If I have a path that hits x for the first time, then for every path that ends above x, there's one that ends below x. So this, which of course is intuitive in the case of finitely many paths, has a infinite version of it that says that the probability is a half, okay? And this has a very important implication for us, which is, I just walk you through some formula. This is the formula that I wanted to get at. If I have a Brownian motion that starts at 0 and a value which is positive, the probability that my Brownian motion is bigger than a certain value at a certain time, I can write it down as this expression. The probability of my Brownian motion at time t is bigger than x, conditional that the heating time is less, plus the same thing, conditional the heating time is more. Because these are complementary events. So this probability is obviously the same when you add them up, okay? But because Brownian paths are continuous, if Tx is bigger than T, that means that the heating time is bigger than T. That means I couldn't have been, I couldn't be above X yet, because otherwise I have to go from above X to B, and I have to cross X at some point because they are continuous. So that means that the second term is 0, therefore I'm left with the first one. And the first one, which is here, now I use the reflection principle, which was very obvious to us, to have a very important consequence for us, which is that the probability that Brownian motion is bigger than x, conditional that I was already at x, is a half. It's a consequence of the reflection principle. And I can calculate it because this is given to me by the Gaussian distribution. Phi here is the cumulative distribution Gaussian, is the cumulative distribution function of the Gaussian. Right? There you go. And this properties of heating times, we can see that the probability, every Brownian motion will get everywhere. And we can see that sometimes it can take forever to get everywhere. The expectation is actually equal to infinity. Okay? Although we will get everywhere, the expectation will be that it takes forever to get anywhere. Okay? So it's like Toronto traffic. Yeah? Yes. All right. Now the running maximum is a very important quantity for us, which is, imagine you flip a coin +1 -1, and what you keep track of is, what is your biggest score over time, not the balance, but the biggest balance you have had. And you can have an analog of this in Brownian motion. It's expressed like this: is the maximum value of Brownian motion in a period of time, and this is something which we will be able to calculate explicitly. We just need to observe that the probability that the maximum is bigger than a certain value x is the same as the probability that by heating time for x is less than or equal to t, which we already calculated. Therefore, we have a formula for it. It's this one here. This is very important because we will be able to determine the running maximum, the probability of the running maximum for Brownian motion over time. And this is, so imagine the concept of ruin. What's the probability I run out of money in a year? Well, it's a Gaussian. What's the probability I run out of money before a year? That's a different number, and it's given by this expression. Okay, and it will be important for risk management purposes. And I have an example here, a margin call risk. I'll just tell you this. I don't know what I will. Okay, so imagine I have a portfolio that has a profit and loss distribution. It has mean 0 and standard deviation equal to sigma. And imagine I'm trading. You may not know what this is. We'll see that in great detail in a few weeks. But imagine I have some money. I'm trading. Okay. What's the probability that my trade will lose me more than that money I have? A called collateral. What's the probability of that? Well, we have the formula for that. It's here. Okay. So it gives us. It's a modified version of ruin. These things are important, and I know this because I can calculate the probability of the running maximum for a Brownian motion. Okay, so there's a well, I think I'm going to jump. It's 150. I'll tell you this. Other processes. Brownian motion is not the only process which is relevant for finance. The Poisson distribution is important. The Poisson process is important for us. Here I'm just reminding you what the Poisson distribution is. It's given by, it measures discrete events. Brownian motion is good for continuous events. The Poisson process, the Poisson distribution, is going to be good for discrete events. 1, 2, 3. These are the values, right? And this is the intensity beta determines the Poisson distribution that I can have that assigns these probabilities to the occurrence of the integers as expressed in this expression. And the intuition is that If beta is a very large number, then k has to be very large before this number becomes small. But if beta is very small, then this number starts to decrease very quickly. So the consequence of that is that the expectation and the standard deviation of the Poisson distribution is equal to the intensity beta. That's the Poisson distribution. And in the case of, you take this into the processes, well, I have some comparisons here. This is what the Poisson distribution looks like with the intensity is 1. That's when it's 5, and that's when it's 10. That's how it behaves. Okay? You've seen this. This is elementary probability. But now I want to tell you about the Poisson process. It's not a variant of Brownian motion. It's a process like Brownian motion that appears in finance sometimes when it assigns random occurrence of integer events. And it's defined like Brownian motion. We start at the origin. The increments are independent like Brownian motion, but the differences are not given by, the increments are not given by Gaussian distributions, are given by Poisson distributions. That's what they call it, Poisson process. Okay, I have two examples of the processes here where you can see that the intensity is what? In one case it's about 1, in the other one it's about, what's your guess? What's the intensity? 10, 8 actually. Yeah. Okay, you can see that there. See, these graphs are misleading because this one is very peaked, right? So anyway. And with the Poisson process comes a compound Poisson process. And given a Poisson process with a certain intensity and a sequence of independent random variables given by some numbers yk, then a compound Poisson process is the sum of as many of these random variables as the Poisson process tells me. And I have an example here of an insurance company. Imagine an insurance company that receives an average of 20 claims per week, and each claim amount follows a Gaussian distribution of mean mu and standard deviation sigma. Then what is the losses that you can have altogether? Well, the loss is a compound Poisson process where at every point in time, every week you have an unknown number of claims of unknown size, but they are expressed by this. It's a compound Poisson process. That's what you have there. And here we have an equation. We can calculate the expectation and the standard deviation of this process exactly. It's given by what's called Wahl's equation or Wahl's equation. And in our example, happens to be equal to this. These formulas are just, you may have seen this. You probably already know. I don't know. Which means that I can calculate the mean of my total loss and the standard deviation of my losses. Okay? With that, I have other processes, the mean reverting processes, for example, which are a variant. It's an Ito process. This is an Ito process. But here the key in the Ito process is that I have two elements, as usual. I have the drift and I have this, the intensity of randomness. The key is the sign of the drift. The sign has a negative sign in front of the x. That means that if I'm below the long-term mean mu, the process tends to be pushed up, and if I'm above the mean, the process tends to be pushed down. This is used, for example, to describe the evolution of interest rates. If interest rates are high, they tend to come down. If they're low, they tend to go up. In fact, Vasicek is the first one that came up with a model like that. He established a model for the spot rate of interest rates. The spot rate is the same one that you did in your assignment number 1. Yes? Are they
bounded with probability of 1, or can they still grow?
No, I think they can still grow. I think they can still grow. Yeah, that's a good question. I don't know. I think they'll still grow. Yeah. The biggest problem that we have is that they allow for negative interest rates. But we'll fix that. Okay? And that is what I wanted to do before I end. So there's this mean reverting model for interest rates, very popular, popularized, introduced by Vasicek first, but then Hall and White, who are professors at Rotman here at U of T, they made it very popular because they came up with a very efficient algorithm to calculate this model, and every bank started to use that. Very, very interesting. But you see, it's an Ito process which is now a little bit more mischievous, right? But it's great to describe not stocks but interest rates, because interest rates, they have this property, they don't grow forever. And the mean reversion is, but they do allow rates to become negative. That's not a good thing. That's not a good thing. The Cox Ingersoll Ross is a modification of that you see what it does. It multiplies the standard deviation by the square root of the rate. And we already discussed that. I told you this process prevents rates from becoming negative. So round of applause, very good, well done. It's a very good model. But you see, now things get to be very sophisticated. We just climbed the Black-Scholes peak, and now we see lots of other peaks that look even taller than this one. We're not going to go there. We're not going to go there. You can spend a whole lifetime looking at all of these things. I just wanted you to see this, okay? I have more processes here. You can see, as I told you, that as long as the power is bigger than a half, this process never becomes negative. So they are great to describe financial prices that don't become negative, for example. And you can also have Brownian motion with jumps, where you add Brownian motion and a Poisson process. This is what some people, oops, this went too fast there. This is what some people use to describe financial crisis, for example. Good luck calibrating this, very hard to calibrate. But that's another mountain peak. I'm just telling you, it's there, look, and then I'm moving on, okay? We're just looking at all the landscape here. The Heston model, another thing, it describes stock prices like the process we saw here today, except the volatility follows a mean reverting process a la Cox Ingersoll Ross with the square root there so that it's never negative. Good luck with that model. But it's great. Another peak that we see in the distance that is being used for years. And you can keep going and going and going. And there's no end to this galaxy here, okay? So I just wanted to see all the different peaks that we're not going to touch. There's many, many of them. And maybe to end with a comment, which is model risk. We're starting risk management next week. Model risk is you use the wrong model for your analysis. The result of that is what's called model risk. Wrong predictions, wrong calibration of your models. Parsimonious models are great because they use very few parameters, so they minimize model risk from the estimation perspective, but then they may maximize model risk because you end up using a model which is too simplistic. And now it gives you an idea of all of the peaks that exist out there. Some of them very sophisticated to model your data better, some of them very simple so that you don't end up having too many parameters that you don't know how to calibrate and then you overfit the data. And you can keep going and going and going. And on that, I end this, really the first chapter of this course, or the first half. Now we take a reading week break, well needed, because we are abandoning all of this, not just the peak of Black-Scholes, but all the others we could see in the distance. That's gone. Now we're moving to risk management after reading week on Zoom. Okay. Thank you.